All right, guys, so today, section 6.4, vectors and dot products. So guys, it happens this way each year, to be perfectly honest. I'm not surprised if we spend a little bit more time than usual going over question 6.3, day 2. Like I said, it's the nature of the problems that you were doing in section 6.3, day 2. I get it, and I'd rather you feel decent about that stuff before we hand in the assignment. So I do think that it's worth it in that regard. What we need to have our eyes on as far as this week, Thursday, we're going to be testing over the second part of Chapter 6. So 6.3, 6.4, we're going to be testing on Thursday. So that puts us today getting, frankly, as far as we can on 6.4. We'll see how it goes. I think it'll be close. But whatever we don't get through today, we'll finish up tomorrow. If we get through all of it today, great. But tomorrow we've got some review of 6.3, 6.4 in class planned that we're going to be tackling, and then that puts us Wednesday at our group reviews that we're going to do, and then we test Thursday, and then we've got one more day before spring break. We've got some ACT stuff that is coming our way, which I know seniors, you are pumped for. So, but anyways, it'll be a very easy day for you seniors. So anyway, section 6.4, vectors and dot products. I feel confident coming right out and saying that we will have a lot of success with section 6.4. While dot products are a brand new concept, I know that you've talked about vectors in previous classes. You've never talked about dot products before, but literally, if you know how to multiply and add numbers together, you're all set. Again, you will not have any issue once we can mentally get over the hump of understanding how to find the dot product, and once you see it 2 or 3 times, you'll have it down pat. Like I said, it's pretty simple, pretty straightforward. The nice thing about dot products, and you're going to hear me harp on this quite a bit the next couple of days, is that I think that you've already heard me talk about it a lot last week, that vectors, they're not numbers. They're not algebraic expressions or anything like that, but there's a lot of value, as we talked about previously, in that here we have this vector, and we can turn it into this binomial. Or we have this vector, and we can then force it to be on the unit circle, so now we know all of this. Well, what dot product is going to allow us to do is, by calculating what we call, again, this dot product, that's going to enable us to actually assign a real number to a vector. So we can assign a value to a vector, and we can compare them. This vector u's dot product is this, vector w's dot product is that, and that's going to start to tell us some things about these vectors. Remember, it's going to tell us about this empty space that's not really there. So again, pretty powerful in terms of the application. The best part about it, though, once again, is that the calculation is, I don't know, at an elementary level. Like you could have done this calculation, like I said, as long as you know how to multiply and add numbers together, you are set. So the goals that we have in mind, number 1, students be able to find the dot product of two vectors, and use the properties of the dot product. Number 2, students to be able to find the angle between 2 vectors and determine whether the 2 vectors are orthogonal. This is the big one, guys. We need to leave section 6.4, whether that's today before we leave or tomorrow. We need to be able to walk out of section 6.4 knowing how to find the angle between 2 vectors. That's, again, very, very applicable, not only in this class, but in the real world. If you find yourself, going on with any of this other type of applied math and stuff like that, or the physics and stuff like that. All right. Number 3, students will be able to write a vector as the sum of 2 vector components. And then number 4, students will be able to use vectors to find the work done by a force. All right. So sounds like we have a lot of different goals up here. Oh, I'm sure you're going to give me some physics thing here, right? What do you got?
Out of curiosity, other than like addition and subtraction, which of this math that you do in this class do you actually use?
I was going to say there's quite a bit. Like outside of the classroom, I'll just say Pythagorean theorem. You're going to use that a lot. You'll use area formula stuff a lot in your lifetime. Again, a lot of that stuff. But anyway, all right, so guys, the dot product. Excuse me. The dot product of two vectors, it's a real number. I feel like I'm already overplaying this, but I actually can't. It's a really big deal that we have a vector, which is just this kind of fictitious quantity that's out there that you can apply, sure, but again, you can't see it, you can't touch it, but we can turn a vector into a real number. That's a big deal for us. That's going to be very valuable moving forward. So again, the way that we do it, we call this calculating the dot product. It's going to be used very, handsomely to help us to figure out the angle between two vectors. Okay, it's going to be a big deal for us as we go. Now, the dot product, it could be positive, it could be zero, it could be negative. Now, excuse me. I'm just curious, how many different kind of angles do we have, excluding the straight angle? Yeah, 3 different types. You've got acute, right, and obtuse. Wonder if that's related. I don't know. I think they call that foreshadowing, right? Is that what they do? Okay. All right, so guys, here it is, the definition of the dot product. We say the dot product of U. Now, again, we're trying to go very generic here. We're going to call vector U. The component form is U sub 1. The vertical component, that's going to be U sub 2. V, same thing, V1 comma V2. So we have the horizontal components are the sub 1s, the vertical components are the sub 2s, right? All that you do is if you're going to find U dot V, we're going to multiply the horizontals together. You're going to multiply the verticals together, you add them at the end. Like I said before, the actual calculation, super simple, super easy. You could literally go walk into a 3rd grade classroom, 4th grade classroom, and say, hey, can you multiply these numbers together and then add them at the end? Again, the reason why I say that is that you've been doing this for a lot of years. Now, we're applying it in a different way, of course, a much more complex way, but it's take this times this plus that times that. That's how you're going to find the dot product. There isn't a whole lot of, other moving parts or anything like that. Okay, so if we wanted to find the dot product here in this first example, first vector, -3, 8. Second vector is 7, -5. Now, one other thing that I do want to point out, maybe you've noticed it, maybe you haven't. This is not a multiplication situation. Okay, we aren't saying that we're taking U times V. This is actually read U dot V. Okay, it's a little bit different than multiplication. And part of it is just within our own mentality that as soon as we start calling this multiplication, people are going to think, oh, they're like binomials, so I better use the FOIL method. No, that's not dot product. Okay, so for that reason, we definitely want to separate. And when we think of vector multiplication, that's when we have a scalar. We scale a number through, like we essentially distribute that number through. So again, we're going dot product here. So if I wanted to find -3, 8 dot 7, -5, remember what that means is that I'm going to multiply my horizontal components together. So again, I'm going to overplay this problem. We're going to go -3 times 7. I'm going to multiply the vertical components together. We're going to take 8 times -5. So what do we obtain? I do not know why I drew that in component form, because we're going to add them together. All right. So what do I get, please, when we multiply the -3 times 7? And 8 times -5, we get -40. Find the sum, we end up with -61. So right now, at this second, what does that mean? Not much, frankly. In the very near future, that value of a dot product being negative anything, that's going to be very telling. But specifically being -61, now I can compare that to these other 2 vectors that I find the dot product of. Oh, that dot product is -7? Okay, well now I know something in comparison with these 2. But then the next dot product was -250. Okay, well that's going to mean something now. Okay, then the next one was 0, then the next one was positive. All of this is going to start to paint a picture here, hopefully. Ben.
It's like when you do the sum of the products of the parts, they're meant to be similar to matrix multiplication.
It's similar, but not quite the same thing. Because, yeah, matrix multiplication, you have your rows and your columns. But I would say we're kind of, we could force it, I suppose. If we rewrote this first vector, -3, 8, as a horizontal, and then the second as 7, -5, we wrote that as a column matrix or vertical. Like, yes, we essentially are doing it that way at that case. Okay. Well,
With that dot, how will we be able to tell the difference between dot product and multiplication?
oh, it's really easy because there is no matrix multiplication. Like, it doesn't exist. So you won't have to worry about that. All right, so guys, like I said before, matrices, they are not numbers. But we have all of these properties of numbers or algebraic properties that still exist. Now, a couple of these that I would want to point out, like I said, usually we just, snip these little charts out of the textbook and say, hey, there they are. Excuse me. For your usage, again, you can find this on page 431 if you're interested. But I do think that there's value in us talking about especially number one. U dot V is the same as V dot U. Okay? The dot product is what we call commutative. Just like if you took 2 times 3, it's the same as 3 times 2. Okay? Just like if you were adding 2 plus 3 is the same as 3 plus 2. The dot product is commutative. So if you switch the order of the first vector dot the second vector, or again you flip flop that, it's not going to make a difference. Okay? If you have a dot product with 0, your dot product is going to be 0. Okay, now there are going to be other ways to get there as well. We could still obtain a dot product of 0 even if we have this vector times that vector. But again, should that ever happen? Number 3 is probably not going to show up, honestly. But again, basically it's just the first, it's commutative property stretched out. We call this the associative property. That here the order doesn't matter. If we have 3 of these, again, we could alter the order. Actually, no, I'm thinking of something else. I'm down here already. But basically, that dot product, it's going to be treated as if it was practically like distribution. Okay. But the other one that I really want to talk about here is number 4. V dot V, that's going to be equivalent to the magnitude of V squared. Okay, which kind of makes sense when you think about it, but that also might be one that we could utilize as a shortcut. Like if you needed to find V dot V and you already know the magnitude, we could just square the magnitude instead of doing the dot product. Again, we've done the dot product exactly one time, but I think that you already understand that it's not going to be some huge time-consuming process. Again, you're probably saving literal seconds here instead of, if anything, you're not saving minutes and hours worth of work or anything like that. And then finally, distribution is still going to work through that dot product. But like I said, the first and the fourth specifically, those are going to be the ones that probably are going to show up most often. All right, so let's go ahead and try some of this stuff out. We want to let vector U be component form 3, 4, V is -2, 6, W is 1, -1. So what we want to do is find U dot V and then times W. Now remind me, please, when I find U dot V, isn't that going to be a real number? We're not going to get another vector. We're going to get a number. So if I have a number, let's just make it up here. If I had the number 5, W, isn't 5 now a scalar to vector W? That's how that's going to work, right? So the first thing we need to do is figure out what that scalar is going to be by obtaining U dot V. So with your help, I think we can do this all in one shot here. What is 3 times -2, please? -6 plus, what is vertically here? 4 times 6? 24. And with your help, -6 plus 24, we get 18. And vector W, you can clearly see, is 1, -1. So when I scale my 18 through, what is U dot V W? 18 -8. All right, hopefully you're right there with me when I say that this stuff is pretty straightforward, pretty simple. All right, what about U dot 2W? Do you agree that we probably just need to figure out what 2W is before we try to do any dot product or anything like that? Now, we know that U, again, that's given to us, is 3, 4. We want to go dot product with 2W. Does everybody agree that if I scale a 2 through W, that that's going to give us 2, -2? Now we're ready to do the dot products, correct? All right, who wants to give this one a shot? Who wants to walk me through this one? Nobody. Okay, good news. All right, all right. Come on. William, go ahead. What am I going to do first?
So 3 times 2
We get 6 plus
4 times -2 is -8.
6 plus -8, we get
-2.
all right, dot product is -2. All right, guys, how do we feel about this dot product? Every time I come out and say, like, hey, we're going to have a lot of success, I'm always a little nervous in the back of my mind. Like, what if somehow this is the group that just doesn't get it? Okay, that's not happening here, right? Like, we're feeling confident with dot product. We see it. We understand. All right, so this is what we're working towards. And like I kind of anticipated, we're probably not going to have a chance to get all the way through this in these next 4 minutes, but again, at least we're going to have a chance to see it. But this is the formula.